Good morning, boys and girls. Welcome to another lesson on physical sciences, grade 12. Today we are dealing with work, energy, and power. My name is Mr. Sibanyoni, and I'll be taking you through this lesson for today. I hope you have your pens ready as well as paper so that you are able to take down the most important notes and you are also able to work with me as we deal with questions in preparing you for your preparatory examinations as well as your final examinations. Right, we go right away. Now, under work, energy, and power, this is what the examination guidelines tell us that we need to know. So we are quickly going to review this one and then we will move straight into the questions. Right. Under our examination guidelines, it tells us define the work done on an object by a constant force S F delta X. And there we know that's the formula that we actually use to calculate work. Then we must be able again to draw force diagrams as well as free body diagrams. And more importantly, free body diagrams. Remember, under work, energy, and power, we are dealing with forces, and these forces are doing work. They are causing energy changes of objects, and we also use them to determine the power of various machines or objects. And therefore, we must be able to deal with free body diagrams because here we are also going to deal with a lot of forces. Then we must be able again to calculate the net work done on an object. Remember, when we talk about the net work done, we are talking about the total work done on an object. Then we move to the work energy theorem. Remember, you must be able to state the work energy theorem. And it states as follows: the work done on an object by a net force is equal to the change in the object's kinetic energy. Remember, it is not just the work done by a force, it is the work done by the net force. And it is equal to the change in the object's kinetic energy. So that is very critical for you to understand and to be able to state it properly and correctly. Then we must be able to apply the work energy theorem to objects that are placed on a horizontal, a vertical, as well as an inclined plane. And remember, all these planes, they might not have friction or they might have friction. So we must be able to deal with all of those. Are we together? Right? Again, under the work energy principle, work energy and power, we must be able to deal with the conservation of energy when we deal with non-conservative forces. And out of this section, remember important definitions. You must be able to define a conservative force and you must be able to define a non-conservative force. And we will deal with that, my dear learners, as we deal with questions. I'm just highlighting for you the most important definitions of this particular topic. Once more, my learners, we must be able to state the principle of conservation of mechanical energy, a very important principle that we must be able to state. Again, remember, we ask you to define what an isolated system is. And remember, we learned more about an isolated system at the beginning when we started to learn momentum and impulse. And also here, when we deal with conservation of mechanical energy, we must be dealing with an isolated system. So you must be able to define it. And then we are going to solve questions that deal with conservation of energy, the conservation of mechanical energy. And this is among some of the equations that we must be able to work with when we are dealing with problems on work and energy and kinetic energy as well as potential energy. Then the last section on work, energy, and power is the section on power. And the section on power, my dear learners, we must be able to define the term power. And we say power is the rate at which work is done. If not so, you could say it is the rate at which energy is expended. But this word there, rate, is very important. And this is the formula that we use to calculate work. Sometimes we can use this formula. Average power is equal to the force multiplied by the average speed. Remember, this one represents the speed of the object, which is the average speed. And then we must be able to calculate the power output for a pump lifting a mass. It could be a pump that is lifting water through a height at a constant speed. And normally when we deal with this one, this is where we will normally use this equation to calculate the power. Right, so this is more or less what the examination guidelines are telling you you must be able to deal with when you deal with the section on work, energy, and power. Right, we move straight away to the questions. It reads as follows. The diagram below shows a track ABC. So there's a track ABC. The curved section AB is frictionless. Right? Now, as you read the questions, you must definitely underline the most important keywords. And the rough horizontal section BC is 8 meters long. So they have told us that this section AB is frictionless. And therefore, if it is frictionless, it tells us that the system is isolated. But remember, the system is only isolated for the section AB because that is where there is no frictional force. Right. So the fact that they are saying there's no friction, that is a clue to tell you that the system there is isolated. And then the section BC, they have told us that it is rough, and we know that if it is rough, then it means there is a frictional force. Now, once there is friction, my dear learners, we know that the system is not isolated. The system is not isolated altogether. So these are amongst the most important notes that you need to keep as you are reading the question and trying to digest the scenario that you are dealing with. You make notes, and you will see once there's more notes on your diagram, it will become easy for you to understand what is going on. They are saying to us, an object of mass 10 kilograms is released from point A, which is 4 meters above the ground. Now, from there, they are telling us an object is there and it is being released from point A. Now, once we release it, my dear learners, and they are not telling us that it is given an initial velocity of 5 meters per second or 10 meters per second. Therefore, by being released there, it means it was at rest, and therefore at point A, the speed of the object is 0 meters per second. And it was 4 meters above the ground. We can see that. Then it slides down the track and comes to rest at point C. So it moves down, it moves down. Now, when it gets to point C, it comes to rest. Immediately when we say it comes to rest, it means it stops, right? Because it's coming to rest, it stops. It means at point C, the speed of the object or the velocity of the object is 0 meters per second. 1.1.1, we are being asked to state the principle of conservation of mechanical energy in weights. So very critical there. They are telling us that we need to state it in weights. Now, my dear learners, there we have it. The principle of conservation of mechanical energy. Now, my dear learners, this question is always asked. This principle, you must know it. It will be asked, and it is very important. Now, it says the total mechanical energy in an isolated system remains constant. The total mechanical energy in an isolated system remains constant. Remember, it is very important that you state the total altogether, right? It is the total mechanical energy. Now, once you just say the mechanical energy in an isolated system remains constant, we can't give you a mark because that word total is very important. And that is why we are using examination guidelines. We want you to be able to define and state the principles as given there. So the total mechanical energy in an isolated system remains constant, and you just stop there altogether. What you see in brackets here, sum of gravitational potential energy and kinetic energy, it is just to explain further what mechanical energy is. But all you need to tell us is that the total mechanical energy, this part that is highlighted, in an isolated system remains constant. And that is how you are going to get your 2 marks altogether. Right. Also, remember, it must be an isolated system. So you can't omit the word isolated, and this will be a 2 or a 0. Then they're telling us, is mechanical energy conserved as the object slides from A to C? Right? Yes or no? Remember, if they're asking me if mechanical energy is conserved, they're asking me if mechanical energy remains constant. They're asking me if mechanical energy does remain constant when the object moves from A all the way up to C. So remember, in place of the word conserved, they could have used the word constant. And what we know is that from A to B, the system is isolated. And if the system is isolated, then from A to B, the mechanical energy is conserved. But what did we say about B to C? We can see that there was frictional force, and therefore the system is not isolated. So if I check from A up to C, I can definitely conclude that it is not conserved. Why? Because along BC, there is frictional force. The system is not isolated. So the correct answer there must be a no. And we were told we must only write yes or no. And that's how you were going to get your 1 mark. Now we move to question 1.1.3. They're asking us using energy principles only. So now there is an instruction using energy principles only. We can see that the word energy principles has been capitalized. And when it has been capitalized, it means we need to read carefully there. And we must calculate the magnitude of the frictional force exerted on the object as it moves along BC. So we must go and calculate what is the magnitude of the frictional force as the object moves along BC. But we can only do that using energy principles. It means if I try and do this question and I get the correct frictional force, but I have not used energy principles, it means I am going to lose all of the 6 marks altogether. And that's not what we want altogether, my dear learners. So we are going to use energy principles, and we must get the magnitude of the frictional force. Remember, if I want the magnitude of the frictional force, it means here only magnitude is important to be given. If you don't give direction, we are not going to penalize you. Now, we definitely know that there is frictional force here, and I must be able to calculate it. Now, if you check the type of frictional force that we are dealing with here, it is definitely kinetic frictional force. It is definitely kinetic frictional force. How do we know that it is kinetic frictional force? Because the object was in motion. Remember, if the object was static, meaning stationary, and there is frictional force, then it would be static friction. So now we definitely know that we are dealing with kinetic friction. Now, before we go further, my dear learners, remember, you can't go and work with forces without dealing with a free body diagram. It is important that we draw a free body diagram so that we understand exactly what is happening there. Now, let us draw a free body diagram only along BC. So here's my object. Now, with my object, my dear learners, when it starts to enter this part, which is the motion that starts at point D, there is no one that is pushing it. There is no force that is being applied, which is being an applied force altogether, because it is not being pushed and it is not being pulled. The object is moving. Now, what are the forces that are acting? Firstly, the object is attracted towards the center of the earth, and that force will be the force of gravity. The object is on a surface, right? Remember, our forces must be straight. Move that one. Let me do my best to draw it straight there. Okay. I'll have the normal force, which is the force that the surface exerts on the object, and it acts perpendicular to the surface. And then the object is moving towards C. So it is moving to the right. It means the frictional force is moving, rather the frictional force is acting to the left, and that frictional force is the kinetic friction. Now, here, my dear learners, let us look at the forces that are doing work. We can conclude that the normal force is not doing work. Why? Because the object, the direction of displacement is to the right, and the normal force is going upwards. So the angle there between the direction of displacement and the normal force is an angle of 90 degrees. So it will not do any work. The force of gravity is also not doing work because the force of gravity is acting downwards. The direction of displacement is to the right, and therefore it makes an angle of 90 degrees. So these two forces, the normal and the force of gravity, are not doing work. And therefore, the only force that is doing work when the object is moving along BC is the kinetic friction. In other words, if I want the net work done on an object by a net force, it means my net force is actually the magnitude of the kinetic frictional force, because this is the only force that horizontally is not giving me 0. Now, the normal force and the force of gravity are balanced. And if they are balanced, it means vertically the net force is 0. But horizontally, the net force is not 0. So the net force is actually represented by the kinetic frictional force. And because this kinetic frictional force is the only force that is doing work, it means the net work done on the object is the work that is done by the kinetic friction altogether. Now, when we do this one and we try to apply the work energy theorem, we are definitely going to get to the correct answer. Now, let us see how we should have answered this question. Now, what you can definitely do, my dear learners, is to say, okay, let me use the work energy theorem. Now, you would have said, according to the work energy theorem, W net is equal to delta K. And I just want to start it there. And we will see what we would have that is actually missing. Now, if I say W net is equal to delta K, then I need to go and break delta K. And for me to break delta K, I will know that when I see the change in kinetic energy, I see the final kinetic energy minus the initial kinetic energy. And that is half m into just want to make my bracket look nicer. There we go. Half m vf squared minus vi squared. Now, my dear learners, W net is equal to delta K, And when I see delta K, my dear learners, I see half mvf squared minus vi squared, and that will be in brackets because the mass is the same, and therefore I'm going to take it out as a common factor. Now you must be able to break down the formula of the change in kinetic energy into that, right? Then the net work done, my dear learners, remember when I see work, I see F multiplied by delta X multiplied by the cos of theta. And this F, my dear learners, will then represent the frictional force because the frictional force is the only one that is doing work, and therefore it is responsible for the network that is done on the object. And hence I'm going to have the value of F there being the frictional force. So it will be frictional force multiplied by the displacement cos of theta is equal to delta K. And we know delta K is exactly that. Then when I break it down, I will say, okay, I want the magnitude of the frictional force. The frictional force will be F. The displacement, remember along BC, it moved for 8 meters. So it will be 8 cos of 180 degrees. When you deal with frictional force, my dear learners, your theta must be 180 degrees because the object is moving to the right and the frictional force is to the left. So the angle between the force as well as the direction of displacement, we can definitely see that it's 180 degrees because the frictional force always opposes the direction of motion of an object. It's equal to half, right? There's the half multiplied by the mass of the object. Remember, they told us that the mass of the object is 10 kilograms. And that is why there we are multiplying by 10. And now I must substitute Vf squared minus Vi squared. So there must be the final speed, and that must be the initial speed. The final speed is the speed at point C. Remember, the frictional force is only acting along BC. So I'm looking at the motion along BC. It means the motion starts at B, and that will be my VI, and the motion ends at C. That is going to be my VF. So I already have VF, which is 0. So there's my VF is 0 is the same as 0 squared minus then the initial velocity, or rather the initial speed, it's the speed at B. Now, we don't really know the speed at B because my object started at A and it went down the track, right? It went down the track. Now, as my object went down the track, my dear learners, then you should be able to see that it started at 0 meters per second and it went down, and its speed increases. And when it's at that point, it's going to be at a particular speed. It doesn't start at 0. Now, this becomes the question mark. So most of the learners might be stuck to say, but now what is the speed at B? It means you must then go and calculate the speed at E so that you are able to substitute it into your equation. And that is why we are being given this question for 6 marks. Now, you must then check how can you do this? Now you say, okay, B, it's the motion that I get somewhere along BC. Can the section BC help me to get an answer? And we say No, definitely cannot help you to get an answer. You say, okay, let me try motion AB when it started there and when it got to B. And we say, if I want to try this section, one thing that I can try is to use the principle of conservation of mechanical energy. Now, why would I want to try the principle of conservation of mechanical energy? Because it is applicable, number one. And why is it applicable? Because the system is isolated. And remember, we said the total mechanical energy of an isolated system remains constant. In other words, the mechanical energy at any point along AB where the system is isolated does not change. And therefore, the mechanical energy at A is equal to the mechanical energy at B. Or you could have said the mechanical energy at the top is equal to the mechanical energy at the bottom. And that will definitely help you to get the speed at B. And I started here because I know this is normally where you are going to start as learners and you get problems. Now, you then see that, oh, I don't know the speed at B, let me calculate it. And this is where we are calculating it along this section. We say the mechanical energy at A is equal to the mechanical energy at B. Remember, mechanical energy is the sum of the gravitational potential energy and kinetic energy of an object. And that will be at A and the same at B. Then, if you break down EP, we know it is equal to mgh ek half mv squared. And the same applies for B, mgh, and the kinetic energy is half mv squared. Now, remember, I wanted the speed at B. It means this is essentially what I am looking for. Then, remember, at A, the mass was 10. G is a constant from the data sheet. Its value is 9,8. And the height is 4 meters. Remember, it's at A. And the height, we always measure it from the ground to where the object is. And we can see it's 4 meters when it's at A. Plus half mv squared. Why are we getting a 0 here? Because it will be half times the mass, which is 10, times the speed at A. Remember, it was released, it's 0. And that is why half times mass times 0 squared gives us 0. It's equal to, now we go to point B, the gravitational potential energy is 0. Why? Because the mass is 10, the G is 9,8, but when it's at B, it's right on the ground. It's right on the ground, so there is no height. The height is 0, plus at B, half times the mass, which is 10, times speed squared. And this gives me the speed at B to be 8,85 meters per second. And that is why, if I know the speed there is 8,85, it means I know the initial speed. I put it there. There's the initial speed of 8,85 squared. And I get my frictional force to be 48,95 newtons. So this is where the 6 mark was coming from, and it was a multi-step answer. Very interesting. I'm sure you can deal with this one. And this is the easiest method. Now, let us move to question 1.2. It says, a motor pulls a crate of mass 300 kilograms with a constant force. It means the magnitude of the force that the motor is pulling with does not change. By means of a light inextensible rope, running over a light frictionless pulley. So this is the pulley. They're saying the pulley is frictionless. They are not saying the surface is frictionless. It is the pulley that is frictionless. Then they tell us the coefficient of kinetic friction between the crate and the surface of the plane is 0.19. You see what has been given there? The coefficient of kinetic friction. It means they have given me this. They haven't given me the frictional force. They've given me the coefficient of kinetic friction. So don't make a mistake. And it can be friction. You see, it doesn't have units. And we know it is the coefficient that does not carry units. Then we are being asked to calculate. Okay, there's our diagram. We have our motor. There's a rope, which is a light, inextensible rope, and it is pulling the crate. And the mass of the crate is 300 kilograms. There's the incline, and the incline makes an angle of 25 degrees with the horizontal. Now we want the magnitude of the frictional force acting between the crate and the surface of the inclined plane. Now, we want the frictional force. Let us draw a free body diagram along the incline. Remember, when we deal with forces, we draw a free body diagram. Number one, I must have the force of gravity. Number two, I must have the force that is applied. Force that is applied by the motor. Then I must have the normal force. The normal force, remember, it acts perpendicular to the surface. There's the normal force, my dear learners. And then remember, there is frictional force as well. Now, my object remember, this said it is being pulled. It means it is going up the incline altogether. Then, obviously, as it goes up the incline, my dear learners, it means I have the frictional force that will be going down the incline. So this is the free body diagram for the object. Now, this free body diagram is on an incline. And when it's on an incline, my dear learners, remember, this is how would actually give you marks. Would want you to draw it like this, and would have given you 1, 2, 3, 4 marks altogether. But now, my dear learners, this force of gravity, it will be very difficult for you to give it direction because you are dealing with forces that are going this one. Okay. You are dealing with forces that are acting parallel to the incline as well as perpendicular to the incline. So you'd want to deal with the direction in that fashion. So it will be best if I take the force of gravity and I break it into components. But when we want a free body diagram, you must draw the force of gravity as it is and not give it to us in components. So the components will then be Fg perpendicular, and it will also be, I just make my dot bigger, which will also be Fg parallel. And FG parallel, my dear learners, remember it always acts down the incline. Now, what do we know here, my dear learners? We know that the normal force is equal to FG perpendicular. Normal force is equal to FG perpendicular. And we know that if the normal force is equal to FG perpendicular, we know on an incline, FG perpendicular is equal to mg cos of theta. Right. So we must remember when we see the normal, it's equal to FG perpendicular, and that will then be equal to mg multiplied by the cos of theta. So let us go to our answer. Why are we saying the normal is equal to FG perpendicular? Because my object is not bouncing perpendicular to the incline up or down. So this force and this force must be equal. Then if you understand that, it becomes easy. Our answer then, what you should be able to see then is that the formula to calculate kinetic friction is Fk is equal to coefficient of kinetic friction times normal force. And then the coefficient of kinetic friction is there. Remember, the normal force is equal to mg cos of theta. Then you substitute, the coefficient was given, and it was given as 0.19. The mass was in kg 300, g a constant 9.8, cos of the angle of the incline, which is 25 degrees, and that gives us 506.26 newtons. And this is where your 3 marks is coming from. Right. There's the free body diagram that I had drawn for you initial, and this is how we would want it, obviously without this, without that, and without that, and without that. Right. Now they tell us the crate moves up the incline, hence the frictional force is acting down at a constant speed of 0.5 meters per second. And we must calculate the average power delivered by the motor while pulling the crate up the incline. Now, we have two formulas to calculate power. We have the formula power is W over delta T. And the other formula is the average power is equal to F multiplied by the average speed. So we know the speed of the object. There it is. So if I want the power of the motor, I must know the force that is being applied by the motor. So the F there represents the force that is being applied by the motor. And then the speed is not the speed of the motor, is the speed with which the object is moving. Now, this looks very simple because I already have the average speed. So if I can just get the magnitude of the force that the motor applies, then I'll be able to calculate the average power. Now, where you are going to start it, my dear learners, it's actually here where you are going to say F net is equal to MA altogether. There you are definitely getting a mark. Then, according to this diagram, my dear learners, or rather, let us look at this one. These forces, the normal force, use a different pen, the normal force and FG perpendicular. These two forces are balanced perpendicular to the incline. So the net force of the normal force and FG perpendicular gives me 0. So the only forces that I'll have to look at are the forces that are acting parallel to the incline. Although this time, the forces that are acting parallel to the incline, they are also balanced. And if they are balanced, it means the net force is 0. And how do I know that the net force is 0 or these forces are balanced? Because they told me that this object is moving at a constant speed. Then I'm going to say F net is equal to MA. And then in the next step, I will show that F net is equal to 0. Why? Because the object is moving at a constant speed. It moves at a constant speed. It will be mass multiplied by an acceleration of 0 meters per second squared. And that is why this section on MA is what is going to give me a 0. Then I break down what makes up the net force. It is the F applied. It is the kinetic friction as well as FG parallel. So it is the F applied, it is FG parallel. When you see FG sine theta, it means you are seeing FG parallel plus the frictional force. Then remember, when we do the net force, we have to choose our direction. So let us say up the incline, it's positive. Then it means down the incline, it will be negative. Then I substitute. The force that is applied is what I'm looking for. I don't give it direction. It will work itself out. It's F plus negative. Remember, this one is going down the incline. So it will be negative. That is why we said there, it's plus negative this, plus negative that. So positive times negative gives us negative. And then FG, it's 3. FG, we know it's mg. So when I see m, it's 300. G, it's 9,8 sine of 25 degrees. Positive times negative there gives me negative, and the frictional force we calculated is 506,26 is equal to 0. Then if you work out the applied force, it gives you a magnitude of 1,748,76 newtons. Then when you have the magnitude, you go and substitute into this equation. Average power is the force of the motor times the average speed. The force of the motor is the force that is applied multiplied by the average speed of the object, which is 0,5. And this is going to be equal to 874,38 watts when it is rounded off to 2 decimal places. Altogether, my dear learners, so this is very important. Remember, the unit for power is watt. And if your answer doesn't have units, then you are not going to get any marks altogether. And this is how you would have had all the 18 marks from this particular section of the work on work, energy, and power. Now, thank you so much for joining me. I hope that you are really working hard in preparing for your preparatory examinations for physical sciences, for those that haven't written, but for those that have written already, I hope you are preparing thoroughly for your final examinations, which are very much close by. They're actually starting in the next month. Thank you so much and enjoy the rest of the day. Goodbye.